ionization energy is the minimum energy, usually in kilojoules per mole, required to remove electrons from gaseous atoms in their ground state. So the amount of energy required to remove a mole of electrons from atoms. For example, this outer electron here. Now, ionization energy is dependent upon how close the electrons are to the nucleus. If electrons are far from the nucleus, if there's a great distance between the electrons and the nucleus, then there's a small energy required to remove those electrons from that positive charge. Yet, if there's a short distance, there's a greater attraction between the particles, and it requires more energy to remove those electrons, all according to Coulomb's law. So it's easier to remove this outer electron than electrons closer to the nucleus. Lower ionization for this far away electron. But another factor that affects ionization energy is the effective nuclear charge. Now, this electron is attracted to the protons in the nucleus. The more protons there are, the more attracted it is, and therefore the more energy required to remove that electron. But there's also some repulsion of this electron, or between this electron and some inner or core electrons. So the effective nuclear charge is the attraction to the nucleus minus the repulsion from those inner or core electrons. We can see that as we go to the right in the periodic table, there are increasing numbers of protons in the nucleus, but the same number of inner or core electrons. Hence, there's an increasing effective nuclear charge. And because of that, because of the greater attraction between the electron and the nucleus, there's a greater ionization energy, the energy to remove that electron. So as we go to the right, there's increasing ionization energy. And as we go down, though we keep about the same effective nuclear charge, there is a increasing radius between the outer electron and the nucleus. If the electrons are further from the nucleus, then it gets easier and easier to remove them. There's a lower and lower ionization energy. So there's a decrease in ionization energy as we go down the periodic table. So you might add to your postcard, in the top right-hand corner, there's high ionization energy. And in the bottom left-hand corner of the periodic table, there's a low ionization energy. Now, by the way, we can define how metallic an element is by its ionization energy. The most metallic elements, like francium and cesium, have the lowest ionization energies. And as ionization energy increases, as we go up and to the right, we become less and less metallic and more like a non-metal. So these high ionization energy things like helium are not metallic much at all. All right, so the next part is just for college and AP level students. There are varying amounts of ionization energy. We were just discussing first ionization energies, the energy required to remove just one electron from the atom. But there are also further ionization energies as well. The ionization energy 2 is the energy required to remove an electron from an ion which had already lost one electron. So from an ion with a positive 1 charge. And the third ionization energy is the energy required to remove a third electron from the atom, or an electron from an ion with a 2+ charge. Now, ionization energy for the third ionization energy is greater than the second ionization energy and is greater than the first ionization energy. As we remove more and more electrons, the ionization energy increases because it becomes more and more difficult to separate the electron from the now increasingly positive ion. If there are just as many protons but fewer electrons on these ions, there's greater attraction of the electron to the nucleus because there's less repulsion from the nearby electrons. So it's harder and harder to remove electrons from increasingly positive ions. Now, we can kind of discuss the ionization energies, 1, 2, 3, 4, etc., for a variety of elements. And in fact, from the ionization energies, you can identify what element you have. Take a look at lithium. It's 520 kilojoules to remove a mole of electrons from lithium atoms, just to remove the first electrons. This is fairly low as an ionization energy. Lithium has a low first ionization energy, but yet an extremely high second ionization energy, and then a high third ionization energy as well. You can see that there is a dramatic and almost exponential increase in ionization energy as we go from the first to the second ionization energy. It's fairly easy to lose one electron. To take lithium, which was 1s2, 2s1, and to remove one electron, that leaves a noble gas configuration. That is less destabilizing than to remove an electron from the noble gas configuration lithium ion. Lithium ion Li+ has a 1s2 configuration. It is quite stable relatively, and it is very difficult to remove an electron from that to do the second ionization, because that negates or gets rid of the noble gas configuration. Yes, it's easy to remove one electron from lithium. That makes it just like helium, a noble gas. But it's really hard to remove a second electron from lithium, because that makes it just like hydrogen, which is not a noble gas. So low first ionization energy, high second ionization energy. Take a look at beryllium. Actually, first I'll note, please see, yes, let's mark these large increases in ionization energy. Take a look at beryllium. It has a relatively low first and second ionization energy. Yet the third ionization energy is almost 10 times higher than the second ionization energy. It's relatively easy to remove 2 electrons, because removing 2 electrons from beryllium makes it just like lithium and then helium. Easy to get that noble gas configuration, but really hard to lose yet another electron and to be just like hydrogen. So this group 2A element loses 2 electrons easily, and this group 3A element, boron, should lose 3 electrons easily. Take a look at boron. It is easy for it to lose, let's see, 1, 2, 3 electrons to be just like helium. Low, low, low ionization energies until the 4th ionization energy is, again, almost 10 times the 3rd ionization energy. Dramatic increase in ionization energy. Make that mark. If the mark is between ionization energy 1 and 2, you're dealing with a group 1A element. If it's between ionization energy 2 and 3, you're dealing with a 2A element. 3 and 4, a 3A element. So now perhaps you could figure what element you're dealing with here. Let's say it's easy to remove a first electron, but there's a dramatically higher second ionization energy, probably a group 1A element, perhaps lithium, or in this case, it's sodium. Look at this, low, low ionization energy, much higher ionization energy. Probably must be, if it's easy to lose 2 electrons, it must be in group 2A. That might be magnesium. Yes, so you'll learn to make these markings. These markings identify what group the element might be in. Thanks for watching, guys.